These notes will cover the basics of force diagrams. Your first significant goal in this class is to be able to draw a correct force diagram for any situation I throw at you in the first, say, 3-4 months of this class. All right, so what is a force diagram? It's important to get this straight right off the bat, or everything else goes wrong later. Notice the word only. A force diagram has only one object. It's not a diagram of the forces between a bunch of objects. A force diagram has only one object of interest, and if you draw any other objects in it, that's okay. You just can't worry about what happens to them. They can't have any forces on them. Only one object gets the forces. After you've drawn that object, you draw all the forces that act on it from outside. You do not draw what it does to anything else. So notice how focused this is, how it isolates one particular object and looks only at the forces acting on it. And there's a reason for that I'll explain in a second. All right, here's an example. Let's say you have a brick on a floor. We would draw a force pointing down, an arrow pointing down, label it for gravity, an arrow pointing up, label it for the normal force, fine. Or the AP actually recommends you do it this way, and they will often point you in this direction. Just a simple dot, nothing else, and then arrows for the forces and labels for the types. They often call that a free body diagram because you've drawn the body, the object, free of anything that it might be touching. This is actually a better way to think about it when you do physics problems, because the only thing that's relevant to solving the problem, the only thing that the laws and equations care about are the forces that act on the object, what types they are, and which direction they point. The equations don't care what shape the object is, whether it's a box or a square. They don't care what it's made of. They only care what its mass is. And they don't care what it's sitting on, whether it's a table or a floor or whatever. So in a true force diagram, you don't really draw a picture. You draw a dot, and then you draw arrows for the forces. All right, why is it so limited? Why do we focus on one object and only the forces acting on it from outside? Well, it has to do with Newton's second law, and you may remember it this way from 9th grade, F equals ma. But this is really the way to think about it, and this is the way that we'll use it in our class later in the course. Look at all this stuff here and see if you can figure it all out, what every little thing stands for. Okay? This is the capital Greek sigma, which means sum up. So you sum up or add up all of the forces that are external to the object. And that will equal the mass of that object being pushed around times its resulting acceleration. So notice what's what here. This is the mass of the isolated object, the one object that you care about. This is the acceleration of this one object that you care about. But these are forces applied to it from outside. That's why the rules for a force diagram are so strict, because once we've drawn one, we can use it to get quantities to plug into Newton's second law. Only applied or external, and these two terms are really synonymous in this context, only applied external forces can affect an object's motion. This is what says that. Mass of the object, acceleration of the object, but forces from outside applied to the object. You can't make yourself move. If you're in empty space, you can't just push on yourself and make yourself move. You'll just sit still. Right? Something external to you has to apply a force to you to change your motion. So only external forces can affect an object's motion. Perhaps take an object at rest and make it start to move, or stop a moving object, or change the motion of a moving object. Right? So that's why you want to review this several times until you kind of get it straight in your head. We look at one object at a time, and we only look at forces applied to it. All right, so here's an example. Brick on a spring, but not only is the brick on a spring, but it's also in somebody's hand. Okay, and we're going to draw a force diagram for the brick, right? I have to tell you that. Draw a force diagram for this brick. Okay, that's the situation. Is the spring applying a force to the brick? The answer is yes, you can tell because the spring is stretched. It's stretched beyond its normal length. And the brick is touching my hand, so the hand is applying a force to the brick. Okay, so let's draw a quick force diagram for that. Unlike freshman year, I'm going to get you right away used to this AP method of just drawing a dot. Right? And of course, you would draw the gravity force first. Right? Then you could draw an arrow up for the spring force. Then you could draw an arrow up for the pushing force of the hand. And whenever there's an external push or pull that we have some control over, I tend to write F with a P for push or pull. Now this may look very weird to you as a force diagram. It's just a dot and you've got arrows on the side. This is a very common answer on an AP test. A dot with multiple forces going in the same direction, so you kind of draw them off the side of the dot. And that's perfectly okay. That's what they want you to draw as a free body diagram. And it forces you to isolate, to focus your attention only on what's important. The types of forces and the directions they point. Okay? All right. Why am I not drawing the force that the hand or the brick applies to the hand, right? I can feel the brick in my hand. It's making a little dent in my skin. So why not, isn't the brick doing a force there? And isn't the brick pulling down on the spring, right? The brick's pulling down on the spring. What about that force? Why isn't that in the diagram, the kind of brick on the spring force? And if you were wondering that, you have to go back to this. We only draw the force. First, we pick an object of interest. And in this case, I said it was the brick. Someone may have to tell you that. On the AP test, it'll be. This is an actual question on the AP test. We're learning how to do a question on the very first day of class. Draw a force diagram for the car or the plane, that sort of thing. So here's draw a force diagram for the brick. As soon as that is specified, the rest falls into place. That means the brick, and you only draw forces acting on it from outside. If you say, well, what about, doesn't the brick apply a force to the spring? And the answer is yes, but it doesn't go on this diagram. That would go in a force diagram for the spring, which you are not asked to draw. Say, well, doesn't the brick apply a force on the hand? Yes, but that's not on this diagram. That would be on a force diagram for the hand, which you are not asked to draw. And finally, there's a gravity force. Right? We said earlier that every time there's a force, there must be a Newton's third law pair. If the Earth is pulling down on the brick, isn't the brick pulling up? Where's that force? And the answer is, there is that force, but it does not go in this diagram. That would go on a force diagram for the Earth. Okay, final note here. What if you care about two objects? What if there are two objects of interest? And here's an example problem straight out of the big packet of force diagrams. Same kind of problem could be on an AP test. We have two boxes on a smooth floor so friction can be ignored, and a pushing force is applied to this box. A rightward pushing force is applied to box A. Someone's got their hand on box A and they're pushing on it. Draw a force diagram for A and a force diagram for B. I strongly recommend you do not just try to draw arrows all over this diagram. This is a picture. It's not a force diagram. I recommend you do this. Draw the two objects completely separate. And you may say, but they're touching. That's okay. This is a force diagram. It's not a picture. A force diagram is a mathematical tool that we use so that we can apply Newton's second law to each of these separately. So this is not a picture, it's a force diagram. Now let's start drawing forces. Now make several points as we draw this. Why would that be bad? What I just did is not good, and if you did it, I would take off points. It's not because I haven't finished. It's just so far, I've already made a mistake. Okay? And the answer is by using exactly the same symbol for these two gravity forces, I'm saying they're the same. You will lose points from me. I will take off points if you do this. You say, well, I know they might be different. No, you have to tell the reader that they could be different. So I like to put like an A here and a B here. Likewise, for the normal force, I have to add an extra subscript because this normal force is not necessarily the same as that. Because you're going to take these letters and you may plug them into equations. And you might say, well, I'll just plug the numbers into equations. No, it's AP Physics C. Sometimes an entire problem, the entire page, is just letters. It's not always, but sometimes they like to give you a problem where they don't give you any numbers. They want you to manipulate symbols. So if you put that these two are the same, if you left out the A and the B, that would be wrong because these two forces are not necessarily the same strength. Okay, we're not done because I haven't added that one. Now this is a picture. So the arrow is pointing at the object just like a push would be in real life. But we all make an agreement. Even if the push is applied on this side, to make them easy to look at, we draw force diagrams with all arrows pointed away from the center. Because the only thing that matters with a force is how strong it is and which way it points, and its type. So this shows which way it points, which is to the right, and I'll label it FP. So remember, a force diagram is not a picture of what's really going on. We know that this push is actually applied here, but that's not relevant to the physics. That's not relevant to the calculations. All that's relevant is which way it points, and what type it is, and how strong it is. So this is a force diagram. It's not, if you draw an arrow over here, it's not strictly wrong. I won't take off points, but I'll strongly recommend you draw it like everyone else does. Okay, now if you might think we're done, you'd be wrong, because there's one more thing going on. You have to picture what's going on, no friction, and this thing starts moving. Right? You push on this, it's not going to sit still if there's no friction, it's going to move. And A is touching B. This is in our rules for forces. Sorry, this is in our rules for forces. B is touching a flat object, and that's A. So that means A is applying a force to B. Which direction would that force point, the force that A is applying to B? It would point to the right. Since it's a flat surface, strictly this is a normal force, and you could put an N here. But I know it's a normal force. I'm not going to make that mistake. I do this, and I let you do this. I call it just FAB, the force that A applies to B. All right, are we finished? The answer is no. The last force here is the easiest one to miss. You have to use, it doesn't pop out at you from the situation. You have to think of Newton's third law. And that's one of the reasons I encourage you to write FAB. It may trigger that idea of Newton's third law. If A applies a force on B pointing to the right, then what? Then B must apply a force to A pointing to the left. And it has to be exactly the opposite direction and the same exact strength. Since these two have to be exactly the same strength by Newton's third law, you must use exactly the same symbol for both. You can't call this like 1 and that 2 and say, well, I knew they were equal. No, you must use the same symbol for both, because if these go into equations, two different equations, we want to know this is the same exact value so that we may be able to do a substitution, solving simultaneous equations, or do what some students call a cancellation, like divide one out. So you must use the same symbol for these two, because this results from Newton's third law. They have the same strength. This force here may strike you as very weird. And I don't want to do a demonstration in this video, but I can do one when we're as a class. But if you imagine that this is a big pillow and this is a rock, what's going to happen right here? The pillow will crumple right that way. And we have to explain that crumpling by a force, and that's this force. That's B pushing on the rock, pushing on the pillow leftward, and that's why the pillow crumples in the Newtonian explanation. And you can see here why I say that physics doesn't always feel like common sense. And in common sense, we might say, well, the pillow is soft and it kind of wraps around the brick. Now, who cares? That's not, I didn't use the word force. I didn't draw a force. I didn't say a type of force. That's not Newtonian physics. The way we explain that crumpling in Newtonian physics is if A applies a force to B, B applies a force to A.